All right, hi everyone. I'm Andrew. I'm a visiting researcher at Flashbots and Cycles. You may know me for being one of the bold posters about trying to get everyone excited about SGX over the past couple of years in the Web3 ecosystem. I'm told, and from that survey I can tell that everyone here is already interested in TE, so I don't have to do the thing that I normally do. I can go back to what I feel more comfortable with, which is complaining about the wrong ways in which to use it. Much back to my more comfortable zone. I have a few goals for this talk. I do want to convey what I think is a call to action, which is I think we have a really unique opportunity now that we're all interested in TEs and see how much interesting things they can do for Web3. I think we have the opportunity to build a really compelling stack that is essentially going to become the stack that everyone, whether they're in Web3 or in other non-Web3 uses of TEs, they would still want the Web3 integrated components of it as well. So I think this is a really important thing to basically rally all of our values and intentions along. But I want to point out a bunch of things that I think will go wrong. So part of what I want to do in this talk is summarize what I call the tech debt package, which is a handful of the things that are somewhat in the weeds details, but that we need to address to get the full value out of these. So before I get to the negative stuff, I do want to portray what is, I think, maybe aspirational, to some degree already real today. What's the value that TEs bring to Web3? And what you get with a trusted hardware environment is essentially integrity guarantees automatically through the remote attestation they provide, and you get confidentiality guarantees pretty much built in as well. And so what this is that you can run any existing software that you have through a TE and you get something that has these guarantees through it. So if you take any smart contract VM and you run it in a TE, you get a programmable privacy smart contract system. You can do this for any of the different smart contract VMs. This carries over then when you take apps that are written in smart contracts for these VMs and you run them in the smart contracts in a TE, you get a private version of those. If you run an ordinary AMM like Uniswap in the Oasis TE version of it, you get a dark pool. If you run a compound lending thing inside a TE-based smart contract, you get a margin lending where you have snipe resistance against your different portfolio positions. Anything you put through a TE comes out a little bit different and generally better. There's no real reason not to do it. If you put a builder and run it in a TE, you automatically get a guarantee that all of the simulation rules and ordering rules are followed, that any bidding or refund rules are followed. You'll hear more about this from Shay in the case of our builder running in TDX from Flashbots, and that the relevant privacy things are guaranteed. TEs can finish your L2s for you. If you put an L2 sequencer that doesn't have its fraud proofs built in yet, it comes out of Validium with proactive guarantees of what you would want the ZK for. You now get the remote attestation from the TE giving it to you. If you already have a ZK rollup and your provers working, then when you put it through a TE, you get a multi-prover system with a second defense in depth guarantee from the trusted hardware. If you put something that's MPC or FHE and you run all of that in the trusted hardware, then you get collusion resistance added to your MPC. That's something that only trusted hardware can provide. In general, if you take any Web 2 application and you put it inside a TE, it comes out a cool Web 2 application. Because you can very easily do OAuth and TLS kind of things, both server and client side from the trusted hardware. So you can make Web3 liquefied, resellable versions of any API access that you have in an ordinary Web 2 world. I want to give a little bit of an overview of the relevant software stack and make a bunch of points on where I think there's a role for Web3 to change the software, or at least set some of the values that hopefully are reflected in the software. So trusted hardware is something that is, it comes from, the support for this comes from hardware vendors. So this is something that NVIDIA and Intel and AMD include as a feature at the low level of what their hardware interface offers. On top of that are software stacks like Grameen is a libOS. There's lots of different SDKs like Fortanix, and there are confidential virtual machine systems as well. These basically are exciting because they allow you to import legacy code. That's the thing that really made all of that kind of simple story. You just put it through a TE and it works. That's possible because if you use the software interface, you can run existing legacy code packages that were not designed to run in a TE, but because these interoperability layers are sufficiently good enough, without too much effort or a predictable amount of porting effort, you can get legacy code to run within the trusted hardware, and that's what's so great. So this part is inherently provided by the hardware providers, although I'll come back to that with OpenTEE stuff in a little bit. The rest of the software packages that are built on top of this, sometimes there's some input from them from the hardware providers, like Intel contributed a bunch to Grameen, for example, but it's a separate software package. These software layers are right now mainly provided by what I'll call traditional open source projects. So they are open source, like the Confidential Compute Consortium is one of the things organized under Linux Foundation that produces a bunch of these. So there's nothing wrong with this, except that there's a bit of a difference in trust model that's different than what we want in Web3. And so I think the most important thing is we need to convey what are the values that we want to see in these software stacks and either influence or take it under our own to do the interventions of software design necessary to bring our values to it. So the main thing that these software providers give you is that your sysadmin doesn't have to trust the cloud because you can outsource your computation to the cloud. The trusted hardware means you don't have to trust the cloud. That's great. But it's not quite what we want, right? So what we want is to say the users of your system don't have to trust you, the app developer, or the cloud, right? The cloud and the app developer in our world should both be not trusted, right? It's a little bit of a shift in perspective from the dominant mode of thinking about how trusted hardware is used anywhere else. In short, what I think, and what we're starting to do, I think you see this in say the swap design and also in ports, which Ethan will present on, is we can have our own blockchain layer that basically addresses some of the pain points that show up here, not just because of our values that we want it this way, but also our problems that are pain points like key management and redundancy. Basically, if we had a software stack that integrates blockchains for the things that without blockchains you can't do a good job of, this would be something that is, for any application using trusted hardware better than what the existing software can do. So a bunch of tasks that relate to this kind of final area of the stack of how do you orchestrate a whole bunch of different enclave nodes running, how do you do failover between them, how do you prevent replay attacks and race conditions from managing them. This all goes under the category of orchestration and coordination of nodes, basically. These all benefit from blockchains as a way to do them. So actually integrating blockchains into the software stack is a really good way to proceed. I summarized this difference, but maybe it just bears repeating. The main thing that we want in the Web3 and decentralized world is that users and apps don't have to trust either the software developers or the cloud. This could be don't trust, verify. And it's just a slight difference in perspective than what the current approach to trusted hardware software stacks give. Okay, so now's the part where I want to dig into talking about a couple of in the weeds topics. Hopefully this is educational, or you can argue about it even. I call this the tech debt package because I think that these are all things that we can address, but we need to go and address them. They're not all new things to point out. These are the kind of things that have been accumulating and we haven't addressed them yet. I think this community is the right one to do it. It won't necessarily come upstream from like Intel solving all of these for us or enterprise software stack solving it for us. These may be things that we are the ones to bring. So I will talk about each of these in a bit. The first one I want to talk about is why, even though Intel has done their job, we still are leaving Intel as a party in the middle of the attestations, even though there's no reason it has to be this way. So the story here, maybe some of you are familiar with like the first version of SGX remote attestation called DPID. And it had this kind of flow. There's a part called the provisioning flow, and this is kind of inherent, so we're not going to try to improve on this, but basically the first time you use SGX or TDX on your chip, it has to do some interaction with the Intel service. If you haven't used any SGX app, it won't have done. The first time you use an SGX app, you have to do this. But this only happens once per chip. And you have to do this regardless of which application you're running. The next bit is that you actually now have an app that needs to do remote attestation on your chip. So your app requests it from your chip, but in this original legacy one, it's now deprecated. So this is the way things used to be, that are not now. It used to be that you would then have to go request a signature on your attestation from the Intel service. This requires you to have an API key and a developer account. You get the signed report back. Everyone disliked this a lot, so this got changed. Intel actually really got, this is a meme quote from this SGX Explain paper from long ago, I think nearly 10 years ago now. At the time, you needed to have a business contract with Intel in order to use SGX in production mode. So Intel was really in the loop, and the flow of that deciding that you had to go to Intel and get your thing signed. So they responded to this, and they switched from EPID to DCAP, which gets rid of this problem. To me, this is a great thing, and they did their part. The way that DCAP works is that now you get an attestation directly from your chip. The catch is that you have to get intermediate certificates. Maybe I'm not explaining this then super clearly. There's a root certificate from Intel, that's the signing key, that's the root key for remote attestations. And your chip generates, just like in TLS, you have root CAs built into your browser. On chip, you get a remote attestation, which is signed from a certificate that was signed by a public key that was signed by the root key from Intel. And your chip just automatically can produce this. You don't need any interaction with Intel for it. But all the intermediate certificates on that chain, you have to get them provided by some software called a platform collateral caching service. And the default reference implementation of this, again, goes and fetches it from Intel. And so if you set up DCAP on your device and you just use this default reference software, you'll still be going through that flow where you have to make a developer account with Intel and get an API key. Maybe the software vendor just passed it along to you, but then that becomes a point they can cancel that account and then those API keys won't work. So this is a completely unnecessary software thing left over. We don't need Intel to help us change this, because Intel's already provided the raw level from this. This flow of requesting these platform collaterals doesn't require you to disclose which application you're using, doesn't require any specific details about your computer other than like a processor type. So the obvious thing that we should be doing is changing it so that instead of the default reference one, which just happens to contact Intel because it's just the Hello World program, we can make our own that fetches these from some transparency log intermediary. Like you have a blockchain acting as a mirror for all of these certificates, and we can fetch those without having to tell Intel which app you're running. You can get it from your own light client or however else you want to do it. So to me, this is something that's really interesting because I think that Intel's already done their part by giving us the what we need from the processor to be able to do this better job of cutting them out. But we've kind of left the software still, unfinished. And maybe it's not an issue for anyone else except a Web3 decentralized kind of person, but if you're into decentralization, you really don't want your enclave node runners to have to make an Intel account or for you to share your own dev account API key with enclave users to run. I showed this for this platform collateral example. There's another case that's exactly the same thing with things called TCP infos. It doesn't matter what they are, it's just another flow where right now Intel is in the loop, but they don't have to be. And that's something that we should take into our software stack. The next detail that I do want to say a bit about is about side channels. I think this is something that's not very clearly understood, but basically should be. The very high level view you might have of how an enclave works is that there is this enclave, that is the trusted zone where enclave programs run. That's the point, things in there are generally confidential. The attack model is that the host is trying to steal all of the alpha from the private program while it's running. The whole point of the enclave is to prevent them from doing that. It keeps the privacy and integrity, within the enclave. The hardware enforces this, but it's not perfect confidentiality. There's still some leakage in the form of timing issues, potentially power side channels. So the way to think about it is that the attacker is listening to everything they can get out from the enclave. I think of it as basically like a redacted debug log, because it's not the full debug log of every step that took place in the enclave. In general, stuff in the enclave is hidden. But I think of it as a redacted debug log because you do learn some information about what's happened while the enclave's running. We know that the hypervisor or the untrusted OS manages the disk and the network controller. That's just how operating systems virtualize the hardware components for the software components, including the trusted enclaves to run on. So disk accesses have to go through the OS, so you can tell which block of disk an enclave is interested in. Hopefully it's encrypted, but you still leave which block is relevant. The biggest question is about to what degree memory has this. So just to summarize what I'm concerned about with memory access pattern side channels, you have a program and you are processing your program. right? You have memory for your program code, and then you also have memory for the data that your program code runs on. So every time you access an instruction, it has to go read that instruction from a page of memory for code. If that instruction, accesses 2 pages of memory, it has to go access these pages of memory. The problem with the OS in the case of SGX or the hypervisor in the case of TDX or AMD SEV is that the hypervisor or the OS is responsible for managing memory, the mapping from virtual memory to physical memory if you're, know OS things. So in general, there's a mapping from virtual memory to physical memory, and this bypasses the OS when it's all there. The processor directly reads the RAM and that's it. But one of the things the OS or hypervisor can do is basically mark all the physical memory as inaccessible. And then what happens is when the program goes to access it, it wakes up the untrusted attacker with a page fault that says this is the block of memory that the secret enclave process was interested in. That leaks it to the attacker. This means that we should be concerned with the way SGX and TDX work so far that these kind of access patterns are visible to a hypervisor. Whether this reveals something that's actionable information for your MEV app or L2 sequencer with pre-trade privacy, it really depends. So I think this is kind of tough. I think that this is something that's correctable. There's a thing called AEX notify. I won't go into any details of this. I think this is something that can be implemented within TDX as well. But there's basically a couple of options. Either we basically can regain the lack of side channels for these page accesses because you can detect when these page faults occur and then just abort and slash the operator if that happened. There shouldn't have been a page fault, so if there was, be suspicious that it's an attacker. If we can do that, then that's great. We would still want to use something called oblivious RAM, which I won't go into any details now for time, but I'm interested to talk more about it, and I'll give you a pointer to a website where a team is working with us to apply this RAM algorithm. You would still want to use oblivious RAM for them really large data sets that don't fit in memory, but you might not need it if all goes well with TDX notify for RAM itself. If this can't work for some reason, or we just can't get to it in time, then you probably, to do mitigations against this kind of side channel, have to use oblivious RAM at pretty much every page access you would do. That would be more expensive and create some overhead, but that's a sound way of mitigating the problem of leaking the switch information about how memory is accessed. So that was side channels. The other thing that I want to talk about a bit, because I think this will have to be a longer conversation because it's, I think, tricky what the mitigations are to it. But it comes back to this idea of how are the things that we want to offer to our users as Web3 decentralization maxis different from how ordinary cloud people think about it. You need to have software upgrades in pretty much every system. I mean, what raw attestation gives you is you can say, I'm trusting my sensitive data with just this particular enclave. This is the hash of the program code, and so only this program code that I specify is able to compute on my sensitive data. But practically, you need software updates because there can be a bug in that software, there can be new features that need to be added. All right, so this is then going to be too rigid. Everyone would have to go resubmit their data if there was going to be an upgrade. That's impractical. The simplest alternative, and I point this out because this is the case still today with Secret Network in particular, is in a way the worst case and not really consistent with what we want out of Web3. So you can say, to be more flexible, instead of saying only this enclave of this program hash can compute on my sensitive data, you can say only programs that are signed by the app developer can compute on my sensitive data. The problem here is that then this basically gives full control to the app developer, because now the app developer could just sign an enclave that completely outputs all of its sensitive data. There's no way you can tell that had happened. There's no real defense against this. So this is a really undesirable outcome, but that's the first thing that you would try to do if you know that you need the flexibility of software updates. The better approach, which is at least partially the case already in Fala and Oasis in particular, is the idea that you might want to basically offer rights or guarantees to users that you can use the trusted hardware to actually enforce these guarantees and let users exercise their rights. So you can say, I'm not just going to trust an app developer, but I will trust a smart contract that implements some DAO logic, and anything that the DAO says is allowed to compute on my sensitive data, I'll allow that. So now the developers can propose updates, but they have to post them on a blockchain, and then some rules enforced by the blockchain have to be involved in approving them. Now, the things that we can provide that are rights to users are things that limit, even just because it's on a blockchain and developers were involved, can you do even better than that? Yeah, I think so. So for example, you might want users to be able to opt out of changes to the privacy policy. So it's already a good standard in just ordinary smart contracts with upgradability that if you want to make an upgrade to sensitive contract code, it goes through a pending notice period, so users get to complain about it before the upgrade takes place. We can enforce that by having the enclaves follow blockchains as part of their management and orchestration process. So you can stipulate things enforced by smart contract that any updates have to go through a notice period, and even that users could have the chance to opt out and cancel their sensitive data if they don't like the change to the privacy policy that's coming. So I think this kind of thing is super important because this is the kind of functionality that's most aligned with, I think, our decentralization values that don't on their own automatically show up when you just run things on existing trusted hardware software stacks. So just to summarize where I think Web3 fits in, I think it's really clear that we can be involved in proposing a more decentralized approach to managing keys, managing upgrades, and orchestrating lots of nodes as they're deployed. These are a great fit for blockchains, and I think we should be the ones doing essentially that software development stack. But I think the really thing that's important about our community, and so we should be prepared to do, is if there are other centralizing tendencies, we should be prepared to write software interventions that get around these. So for example, the thing I mentioned about side channel defense, I don't necessarily think it's Intel's job to just obliterate all side channels for us. They're pretty clear about where their boundaries are, and it doesn't include resolving all of those. But it probably includes giving us the software tools that we need to do it. If the SDKs or libOSs aren't doing those already for us, then I think that this is within range of software we can write that can fix this. We can bring side channel defenses at a lower layer if we need to. And I'm really excited about this emerging movement to do open trusted hardware. So there's a lot of proprietary and hard to scrutinize aspects of the TEEs that we use today. Ideally, they would publish everything, but they don't seem like they're going to. But one of the things we can do is basically create a blockchain native hardware stack alternative that might be open source in this way and might solve some of the things that the Intel chips aren't designed to do on their own, like provide physical tamper resistance or the ability to analyze a chip and see how it's constructed and that it matches a step. So I won't say more about the OpenTE project, but I think there will be a bunch more discussion about that by the end of the day. We're prepared to, we should feel very strong about our stance as disruptive decentralization builders, so we shouldn't be afraid of any part of this software or hardware stack. We will route around centralization wherever it shows up. How am I doing on time?
You're fine.
I was hoping for something more quantitative.
Time is the quantitative answer is fine. Continue.
Okay. Let me pause there actually, just if there's any questions. I want to switch away from this kind of overall tech stack thing to a kind of specific high concept thing that I am interested in, but it's maybe more of a divergence. Yeah, please.
So when you say the ability to examine the chip, sand it down, let's say, see what the logic is doing, how would you actually propose to have a level of logic transparency? What would the hardware design level changes be to that?
Yeah, no, this is really tough, and I don't have slides, I guess, here on this deck to talk about it, and I think we'll have more hardware-oriented discussion maybe towards the end of this, but in a really short thing. The biggest thing that's on my mind about this is that there's a fundamental tension between tamper resistance on one end and ease of analysis on the other end. So even if you have an open source reference spec of how your trusted hardware chip's supposed to be made, the problem is, you have this open source design and you have this chip that you're communicating with over, network connection. How do you know that it's an instance of the open source design? The best thing I think you can hope to do is have destructive analysis. So you might commit to a large batch of these produced chips and then send half of them to analysis, or maybe in a public ceremony at Zuzalu or something, do this analysis in public where everyone can watch the process. And the goal is that if they were not built according to the spec, then you find that out during this destructive analysis. I keep saying destructive analysis because if you could see every trace on a chip and analyze it well, that would also be how you would get the secrets out of it while it's running, which is what you don't want to have to do. So do you want more analyzability or more tamper resistance? They seem to go against each other. So I don't have a good answer to that. I think this is like an open challenge for not even just logic and circuitry, but like for microarchitecture, but even like materials science. What's a good way to actually build chips that work like this? So that in a nutshell is what I would expect. I think it's not infeasible because one of the options you can do is basically, if you detect that an analysis is happening, delete all the secrets on it, like a tamper evident thing that self-destructs and self-destructs the secrets that you want to keep within it, but still allows you to analyze that it was made to the spec. I think you may also need to co-design the hardware plan with the analysis that you have in mind, which just isn't something that anyone's had as a design goal in hardware.
Thank you.
Okay, so I will just say a little bit about this concept that I'm excited about. So the main viewpoint that I've had and worked for a while is how to basically do published mechanisms that run in an enclave connected to a smart contract. So the main project I've worked on is the Sura TEE coprocessor. So it's a EVM VM and a light client for Ethereum running in an SGX, and that's all. And then it exposes through some extra precompiles things like remote attestation, so smart contract developers can access them. It's kind of like Ramine, but for Solidity. You can access SGX features from within Solidity, and that's how you can build auction applications and stuff using this. This viewpoint matches this original story of Suave, which is about a contestable marketplace for mechanisms, because anyone can now write a mechanism that uses programmable privacy, and you'll be able to give the guarantees about confidentiality and integrity that come from it. And to me, I always have in mind like an auction as the canonical application that would fit there. But there's a couple reasons why this isn't the whole story. In particular, one of the limits is about composition. So users get to decide which applications they'll trust. Those applications get to decide which other applications they might peer with or allow bids and data to share between. But other than choosing not to use the application, it's the application designer that chooses which other apps get to compose with. There's another viewpoint that I'm now starting to think is even more interesting. It's not an alternative viewpoint, it's just an expansion. So now instead of only thinking about public mechanisms, we can think about both published mechanisms and proprietary code, but that might run within the same sandbox. And so a story here is that you might have multiple proprietary bots that don't make themselves any guarantees about what they're doing. They're like proprietary bidding strategies, but they might run in the same trusted hardware next to the auction where these bots are participating on. And the thing that I'm most interested in is the idea of thinking about not just auctions, but also negotiation between bots like this. And I think that this is a way of thinking about how more mechanisms might be developed and how they might actually emerge naturally, not just from application designers, but participants who are doing trading like this as well. So for example, you might have solvers and builders that are essentially bargaining with each other about how to merge their data and order flow based on their respective strengths. But this bargaining might also be carried out within a single trusted hardware instance. So to me, this is, I don't have any demo or much concreteness, this is just a very preliminary concept, but to me it's a shift in perspective. So I've gone from only thinking about auctions where it's private data but published code to thinking about bargaining where you might have a published sandbox but private proprietary code and data running within that sandbox. So auctions tend to be structured, so it's difficult to explore that space. Bargaining is basically like free-form auctions. There's already some preliminary cool papers about how LLMs can be good for exploring bargaining techniques. So just examples of what bargaining, this is like iterated, trying to find a mutually agreeable solution between two people. So for example, if you're bargaining over lunch, you could say, well, I really care about this, so why don't you give me a concession on something that you care more about that I don't care about as much. Fairness is an issue in bargaining. You often explain, why you care about something and exchange information iteratively during a bargaining process. Essentially, bargaining is a process that's iterative, where the people bargaining take turns making an offer, either accepting the offer or making a counteroffer, and also disclosing more information to try to convince the other person to accept. And sometimes just making concessions. I'll pay you $10 to keep talking about it in case we don't make a deal. So I think that this is a good way of coming up with stylized examples that might make sense for what you might want to have happen in a world where you have access to this trusted sandbox that supports proprietary code. So just a stylized example of how I think bargaining over order flow might have two sources of order flow that essentially say to each other, they have their bots say to each other within this private sandbox, I care more about picking the top of the bundle, but I'll let you have the second draft pick on everything else except for the top of this. You might need to prove to the other one that the data that you have in your bundle is complementary to the data that they have in theirs. There's no overlaps and no conflict between them. Something that shows up a lot in bargaining that wouldn't, except for TEs, be possible to express at all, but I think now it is expressible and that's really interesting, is limits on privilege data. So you can essentially imagine a data room scoped to just a temporal negotiation between two parties. We'll look at each other's order flow. We'll have our bots look at each other's order flow. If we reach an agreement, the merged output goes on. But if we don't reach an agreement, both of our bots forget everything that they learned from the other bot. And it's not just a matter of promising not to use that data, but actually the sandbox just destroys both of them. They didn't reach a deal, so they don't have the ability to take any data outside the failed negotiation. That in a nutshell is, I think, the potential that I'm most excited about. I probably just leave it at that. I think that's kind of the key idea of something that's new that you get from this perspective, that's enabled using TEs, that probably wouldn't even think of as being possible otherwise. So I'm excited about that. I had another point here, but I'll stop it. So thank you.
So, questions?
Okay, I wanted to ask, what should be like the right analogy to interact from the non-secure world to secure world with the network? Like, should we interact via or think via library standard, or should we think about interface standard? So,
What are the question as I understand it is about how do we think about the interaction between the enclave world and the outside world? I guess I'm not sure. The first thing that comes to mind is I'm really excited about all of these applications that I think everyone kind of is seeing all of these at once, but it's how to, what you can do with Web 2 applications in the trusted hardware. And what's really striking is that even just when you use Grameen, you automatically get the entire TLS stack just imported. So all of the browser certificates or system certificates that you need to be a client of TLS and check who you're talking to, those just come along as part of the, all the hard-coded stuff that gets packaged into your enclave. It includes all those certs, so you can just do an ordinary TLS fetch, and it automatically has your enclave checking the same guarantees that your browser would ordinarily be checking, so that's already quite good. And you get the same thing when running a server from within there, because you can generate a certificate signing request from an enclave and get a signed certificate, but you can show in the certificate transparency logs that there's only ever been one certificate issued for this domain, and that certificate comes with a remote attestation, so you know that private key never left the enclave. So I guess what I'm saying is, at least in that viewpoint, maybe there are other kinds of interactions with the non-trusted hardware outside world, but that story is basically that TLS is already a good protocol. You don't even need a different protocol. Having one endpoint, whether client or server, run in the enclave already is solving the biggest part of that. Others?
Yeah, another question. The question is about, say, if we can have multiple enemy boats, then theoretically we cannot have all the boats running on the same machine.
Not all of them on the
have
same
you-
machine, yeah.
Yeah, have you thought about how like those like a large amount of the bots can be integrated or communicate with each other in which like a way so that they can be like orchestrated to work together.
Yeah, I mean, I think that I'm excited about this co-location of bots that are from owners who don't trust each other on the same hardware, because that is the place where you get the lowest latency and highest bandwidth for bargaining-like behavior. But the way that I thought about it before, and that's still relevant, is you could still do transmission. You can still do this information sharing in a safe way across machines. I mean, I think TLS basically goes back to the right answer. I mean, the raw ingredient you need to do orchestration is being able to have secure channels from enclaves to each other that either both know they're satisfying a common condition that's recorded on a blockchain, or they each just recognize, like, I'm talking to another instance of my exact same enclave. And those over TLS, I think, is good enough. Is there some more to your question then? I feel like that's not a whole answer, but
Yeah, probably even go further, then there would be some kind of like a orchestrator to connect the TEs on different areas. Because I think at least all those TEs shouldn't only run on the same like data center. Then yeah, maybe through the internet, that's the best answer I can get so far.
I think there's two extremes of how to do this. So one of them, and I do think one extreme is closer to how Fallow may do it. So one is to basically have where the nodes are and like the mapping of tasks to nodes may entirely be implemented by a smart contract, and therefore that can do distribution or random assignment or things, or a structured bidding for assignment. So you might get a task assigned to a node based on what the smart contract decides is right for you. The other side is to allow individual users or app developers to say, I want to run on this node. It seems to me that the best argument for the smart contract coordinated one is if you want to impose decentralized geographic diversity, for example, on a bunch of tasks, and discourage co-location. My current thinking is that supporting co-location and individuals choosing to appear near each other isn't on its own as centralizing as it seems, because there will still be benefits to co-locating nearer to other sources of data where there's still a value even in co-location, but not co-location of everyone all in one central point, because that's not going to be feasible anyway. But instead making the cost of co-location small enough that it's actually useful to co-locate between different apps in a local region. So you imagine an app is having some smart contract presence, lots of edge mirrors that provide local service that maybe settle or reconcile on chain. You might have apps co-locating at the same local points that provide local service to many users of different applications. It doesn't all have to be in one place. But yeah, there's a spectrum. You either allow users to choose where they want it, in which case there may be a tendency towards everyone clogging up at the same location. You can also impose these through smart contracts. So I think this is the sort of thing that should be exposed from the software stack, the choice of these, and then let application developers either pick a more constrained one or a more allow users to pick one.
Yeah, thanks. That's a good answer.
Thank you. I have this question regarding the security process. How can we protect the TE attacks from the sidechain attacks, for example, timing attacks or other attacks?
Yeah, this is a great question. So the question is how are we going to protect all of these programs from side channels?
Right.
And this is especially the case because the libraries, including the ones that essentially, the promise that Grameen and the VM things like SCD and TDX give you is that you can take your existing application and it automatically runs in a TE, and that seems like that's the end of it. But they don't say that they defend your application against side channels. And so if it's not done yet, then patching side channels may require as much effort as designing your thing to run in TE from the first place, which completely undermines that advantage. So I'm really worried about reaching a point where everyone settles on it runs in a TE, therefore it's secure, and that's the end of it. I think that would be a really bad outcome, because then we will realize that it's not secure, but everyone will have settled on that. So I really want to prevent that from happening by making it clear that we do need more than that. I think that can be managed at the software stack. So first of all, I think it's fine to just have side channels and say our application doesn't defend against these. Maybe your application can be, maybe your application is not confidentiality sensitive at all, or it has a structured pattern and this doesn't matter. So you don't need any further mitigations if you can determine that your application already is not a problem for these. For other side channels, I think the best way to mitigate this is through compiler passes. And one of the things that you can do, especially with TDX, where it's more flexible, you can run a compiler inside your confidential VM. So rather than thinking of someone sending compiled code to run, and you have to trust where that came from, or try to automatically patch side channels on binaries that were produced without it, you might instead send even proprietary source code into the confidential VM, where it runs a compiler pass that mitigates side channels. I think that's broadly the best way forward. There's a couple of research compilers that I'm interested in, like Oblivion, and there was another that I had in mind to mention. That's the one that's on top of mind. Okay, Viaduct is the other. That basically take a program and they output a side channel mitigated pattern. These aren't it's not like LLVM, and this is like a research language and so a little bit specialized. But that's an approach that can mitigate those. You can say here's a language, here's a description of side channel models, and here's a compiler that obliterates the side channels and only outputs a constant time program with conditionals and no timing issues either. So I think that's going to be the most important way to prevent those.
You just hand it back to the next one.
Thank you for the presentation. In the second iteration of SGX, namely SGX2 or even TDX, Intel has sacrificed the very cheap Windows technologies daily. So even without speaking about side channel attacks, can we have the same trust on TEs as we used to do before in the first generation of TDX, for example? And what are the new vulnerabilities that is brought by this sacrifice?
So it used to be that Intel in SGX1 actually had a defense against physical memory tampering. So even if you had a physical, the most interesting attack is an interposer attack. Do you know what a game shark is? I've gotten mixed feel of whether this analogy makes sense. The most interesting attack model for physical attacks is game shark for your memory. This is where you put an interposer in the motherboard and you put the memory into that. And this thing basically gets to put cheat codes into the memory. It can make a copy of memory, it can replay. It used to be that that SGX was defended against that, but then they got rid of that feature in SGX2 for performance. So you no longer have a defense against that kind of physical attack. The upshot, what that means for us right now, is that it only makes sense to have proofs of cloud as part of our attestation policy. Because that attack is possible, you can replay old values, and you can get that access pattern trace through this interposer, even if the OS is blocking it. So we basically have to rely on the clouds at least to prevent physical attacks. So I think it's a little bit nuanced. I think we basically have to say we're okay relying on, to join the network. It's not like you have to be this particular Google data center to join the network, but I think that we would have to have something that's like you have to provide a proof that your node is in some data center from one of top 5 cloud providers, and it's an SGX and all of that. And then you'd be relying on them, the cloud providers, preventing physical attacks like that from occurring, and you have to hope it's not in their business plan to lie about that and actually put it into the list in there. Being able to actually add the Merkle tree back in if we want it or make it an option, that's a really good example of something that we would probably put in an open TE design that's blockchain native for this purpose, and maybe even just the thread of that is enough for them to make it an option and make it available. But yeah, that's really stuck. It's hard for us at a software level to add something to the platform that fixes that. Short of putting a Merkle tree on every single memory access that you do, which would be more overhead than the original thing. So yeah, that's very much tough, and I think the only thing that's practical right now is essentially to rely at least somewhat on the data centers and cloud operators to at least prevent the physical attacks that was removed.
By physical attacks, meaning that the attacker needs to be present physically side, one side of CPU.
Yeah.
And maybe between hand and phone cameras.
The Menbuster paper is, I think, the most interesting. One of these just for a picture of it. So this is what the physical attacker interposer looks like, right? So that's the little ports tapped into the memory of a motherboard, and then this is the logic analyzer that we detect on it. So this is what it would look like if you see one of these in. I think it would be nice if you have a bare metal thing in a cloud. You should also have like a 24/7 live feed, so you can see your camera feed and maybe detect if someone goes and puts something that looks like that next to it. But yeah, short of that, so the original SGX had a defense against this, and the current one does not have a defense against this. So we have to rely on something else for it.
Thank you.
All right. Well, thank you. This is